Okay, we're going to start with accuracy and precision. So accuracy is how close a measurement is to the true value versus precision is how close a set of measurements are to each other. So accuracy is you're looking at a known value, like for instance, the acceleration due to gravity is always 9.8 meters per second squared. So if you're going to do a lab and you are going to try to experimentally determine the acceleration due to gravity, to test your accuracy, you're going to test how close the number you get in lab is to that 9.81 because that is the known value. Precision is how close a set of measurements are to each other. So if you take, usually we will take 3 sets of measurements, we'll have 3 trials, and so you're going to look at those, however many trials you do, you look at the numbers you get and how close they are to each other indicates its precision. So looking at this dartboard, this first dartboard, all of the darts are hitting the bullseye, and they're all in this very small area, so they would both be accurate and precise. In the second dartboard, they're all within the same area, so they're very precise because they're hitting the same area, but they're not very accurate because they're not hitting that bullseye. Now this sometimes will happen if your measuring tool, usually some electronic device, whether it's a scale or a Lab Pro, if it's calibrated wrong, it sometimes will give you an inaccurate measurement, but they're all the same. And then this last one, they're all very wide range apart, not close to the bullseye, so they'd be neither accurate or precise. In order to determine our accuracy, we use what's called percent error. So I'm going to, let me write this up so you can see it a little better. Oh, that blue. Well, so it is percent equals the experimental minus the accepted. So the experimental is what you actually would measure in lab, the numbers that you get in lab. Accepted is what you would look up, an accepted value. And then you divide it by the accepted because you're trying to see how close you are to the accepted. Multiply by 100 to get your percentage, and that would give you your percent error. Now in labs, you really want to look for a percent error under 10%. That would give you a good reading. You're pretty accurate that way. So with the measuring that we do in lab, we do have to take into account significant figures. So in a measurement, you know for certain some of the digits, but some of the digits you don't. You have to make an estimate, and on the next slide there'll be a picture showing what I mean. So the significant figures are including all your known values and your estimate. So significant does not mean certain. It just means that they are part of your measurement, and they're showing how precise, how detailed the smallest increments that your measuring tool can measure. So for example, on this nail, we have a nail that falls in between 6.3 and 6.4. So we know the known values would be the 6 and 3. We know it's 6.3, and then we have to estimate the next digit. So in this example, they estimated at 6.35. All 3 numbers are significant. The 6 and 3 are known. The 5 is unknown. It's uncertain. It's an estimate. But all 3 are significant as our figures. And the importance of this is that when we do calculations with our measurements, we can't come up with a calculation, a final answer that's a lot more precise, it has a lot more decimal places out than what our measuring tool is, because we really don't know those numbers. We only know one number past our known value. So when we do calculations, it's very important to keep track of our significant figures. So first we have to learn how to count our significant figures. So the first, I have 3 types of significant figures that I call them. The first one being this first one, zeros appearing between non-zero digits. I call these zeros captive zeros. It's a captive zero. Captive zeros are always significant. So sometimes it's not you that is giving, in a problem, it'll give you numbers instead of us actually doing the lab. So we need to be able to count these significant figures to know how our calculation, what our final answer for the calculation should be. So whenever you see captive zeros, they're always counted as significant. So their example here is 40.7. This zero right here, that is in between the 4 and the 7. All non-zero numbers are significant. It's the zeros that are tricky. So the zero there is a captive zero. It's between, so it is significant. We have 3 significant figures. And it doesn't matter how many zeros are captive. Here there's 2 zeros being held captive between the 7 and 9. And so we do count them as significant. We have 5 significant figures. The second type of zero is appearing in front. These zeros, since they come in front, I call them leading zeros. Leading zeros are never significant. So here in this first number, in A, we have 2 zeros at the very beginning of the number, 0.095897. So those 2 zeros at the beginning are leading zeros, so they're not significant. So we only count the 95897. So we have 5 significant figures, not 7 significant figures. Same with B. Doesn't matter how many zeros are at the beginning of the number, all 4 of those zeros are not significant, so we only have 1 significant figure as the 9. Another way you can think of this is if you write it in scientific notation, number B, you would write this as 9 times 10 to the negative 4th. So you can see here I only have 1 significant figure. I don't have to include all those other those zeros in my number. So I have 1 significant figure. And then the last type of zero, 3 and 4 here, those are trailing zeros. They come at the end of the number. The trailing zero is only significant if a decimal is present. Okay, so looking at A and B here, I have 2 zeros at the end of the number. So they're trailing zeros. Trailing zeros means I have to check for a decimal place. There is a decimal place in that number, so I do count those zeros as significant. So I would count 1, 2, 3, 4 significant figures. Same with B. There's 9 zeros at the end. So since they're at the end of the number, I say they're trailing zeros. I have to check for a decimal point. There is a decimal point in this number, so they are all significant, all 9 of them, but plus the 9 gives me 10 significant figures. This number 4, A and B, those are a little trickier. So if you look, 2000, we have 3 zeros at the end. So since they're at the end, they're trailing zeros, I check for a decimal point. In part A, there's no decimal point in that number. So that means these 3 zeros are not significant. Now, that does not mean, however, that I can just ignore them and I don't round that number to 2. I can't just truncate and cut off those zeros. And it's still a number of 2000. It just has 1 significant digit. For part B, they're same number of trailing zeros, but if you look, there is a decimal point now. So there is a decimal in this number, so now they are considered significant. So it's showing that this top number, A, that measuring tool did not have very small increments of measurements. So it might only measure from 0 meters to 10,000 meters or something. And so they had to estimate, oh, it looks like about 2,000 meters. Whereas B, it has a lot smaller increments. They aren't just in 10,000s. So for B, there are 4 significant figures because that decimal point is there. So you really have to be careful with your zeros. So I'll just hit a couple of these. Looking at this number right here, 3,340, I have a trailing zero. I have to check for a decimal point. There is a decimal point, so that means there are 4 significant figures here. But looking at this one, there's no decimal place, so I only have 2 significant figures. It's a trailing zero with no decimal point. Looking at this number, the next number, I have 2 zeros at the beginning. Those are leading zeros. Leading zeros never significant, so I can ignore those. And I have 1 captive zero right here. Captive zeros are 1, 2, 3, 4. So I have 4 significant figures here. On this last number, again, I have leading zeros, not significant. I don't count them as significant. Here, these zeros, though, I come at the end of the number, they're trailing, so I got to check for a decimal point. There is a decimal point right here. That means I do count them as significant, so there's 3 plus the 6 and 7, so that makes 5 significant figures. So like I said before, we do a lot of calculations with these, and we have to keep track of our significant figures. So we have a couple rules. For adding and subtracting, you need to check the number of decimal places in your number. And so we're going to count how many decimal places are in each of the numbers that are being added or subtracted, and we can only use the least number of decimal places in our answer. So you cannot have an answer that becomes more precise, meaning goes out more decimal places, than your actual measurements, than your actual numbers that you're adding or subtracting. So here I have three digits in the decimal places. I have 1 digit here. So even though my calculator will spit out this number to me, I have to look, can only have 1 decimal place here. I have to round this number to give me 1 decimal place. So 7.6 would be the correct answer in the correct number of significant figures. Multiplication and division gives me a little different rule. I can only have as many significant figures as the measurement with the fewest significant figures. So what that means is I'm going to count the total significant figures in my numbers, and I'm going to use the least number. So this first number here has 4 significant digits. 1.2 has 2 significant figures. That means I need to only have 2 significant figures, not counting decimal places, we're counting total significant figures in my answer. So when I plug this into my calculator, I get 3.4008. Now I have to round. So now I have to round to, when I round to 2 digits, I have 3.4 would be my correct answer and correct significant figures. Okay, I'm just going to pick 2 of these to do now. We'll do more in class. Let's see, I think I want to do this one, and I'm going to do this one. So the first one, 83.34 plus, or adding, think about what the rule is. I'm going to end up counting decimal places. My number is 85.77531. So in correct significant figures, I can only have 2 decimal places. This is my least number of decimal places. So I'm going to round this to 85.78. And don't forget units. I have a meter plus a meter, so I have meters at the bottom. That's my unit. Okay, the next one, this one, we're multiplying this time. So 4.934 times 14.3928. So my rule is a little different. I have to count total significant figures. So when I put this into my calculator, I get this big long number. Calculators never keep track of your significant figures. So I have to go back. I have 1, 2, 3, 4 significant figures here, 6 significant figures here. So I have to round it to 4 significant figures. So to round this number to 4 total significant figures, I would have 71.01. And now look at our units. We have a meter times a meter. We'd have meters squared as our unit. And last thing is the scientific notation. You need to move that decimal point so that we only have one digit to the left of the decimal. And then you have it times 10 to an integer. Now there's a couple ways you can think of this. Some people, if you have the number and you have to move the decimal left to get the decimal in the correct spot for scientific notation, then you use a positive integer. And then if you move the decimal right, then the integer would be negative. I kind of think of it differently. I think of it as I know exactly where I want my decimal place. I move the decimal place first, and then I look, okay, to get back to my original number. If my original number is very, very small, under 1, so 0.000002, I am going to use a negative integer because I need to move the decimal left to get it back to the original number. If it is a very, very large number, 6 billion, I'm going to have 6 times 10, and then my integer will be very positive. It'll be positive because it's a very, very big number. So if I want to get 6 times 10 to the integer, if I need to get that back to 6 billion, I'm going to have to move it to the right. I'm going to have a positive number up there. So just don't get them confused. Don't stick to one way of thinking, and either way you will get the correct answer.